possible solution, then you know what you need to do. So you save your money, save your time. Okay, with that, I'd like to turn over the presentation to engineer Luba. Please, Luba.
This slide shows the presentation outline. We're going to talk about the pressure-dependent supply, defining what is pressure-dependent supply modeling and why it is important, and how it relates to pressure management, leakage management, and a case study. So in continuous supply, where water, the customers receives water on daily basis. Okay. Okay, the curve is shown in blue. It shows the diurnal pattern of water supply on daily basis. Now, in intermittent supply, the orange line shows the cumulative supply to the customers over the course of a week. And if the customer have sufficient pressure at the connection point to the water supply system, they can get, if the water is supplied through the system on one day for the whole week, and they have sufficient pressure at the demand node, then they can fill their tank for the whole week. But if they don't have sufficient pressure, then there will be a shortage in the water at the connection node to the supply system. So what is the pressure-dependent supply? For most of the models developed in this region, they are dealing with the demand, with the hydraulic models based on demand-driven models, where the customer needed supply is simulated as a constant demand at the customer connection point. But in pressure-dependent supply hydraulic models, we simulate the demand as being correlated to the pressure at the connection point. So when there isn't sufficient pressure at the connection point, customers won't be able to fill their tanks, especially those who are who lives very far from the source or who are on high areas. During supply times, those customers who are at advantageous locations, like low areas or close to the supply source, they can fill their tanks, while customers at the disadvantageous locations will suffer from poor supply due to the low pressures at the connection points. So they may not be able to fill their tanks for the required supply over a week. So what is the pressure-dependent supply modeling? It's basically, as I stated here, it's to relate the demand of the customer to the pressure available at the demand node. So it's the use of the orifice equation, which is Q is equal to CA multiplied by the square root of 2GP. C is the discharge coefficient. A is the cross-sectional area of the orifice, because this is basically the orifice equation. And P is the pressure difference at the orifice. So this curve, the blue curve, shows how the demand at the connection point, the customer connection point, is related to the pressure available at the connection point during the supply time. There is a reference pressure, which is the pressure that gives the demand, the exact demand at this point, and there is the percentage of the pressure available at the node is related to the percentage of the demand that the customer can achieve based on that pressure. And the tabular format is just shows this curve in as numbers. In order to study the pressure-dependent demand supply, we have to consider the size of the nozzles at the customer tanks. This equation, the orifice equation, is reduced to like the emitter equation, so it can be dealt with as Q is equal to K multiplied by B to the power 0.5. So it's basically an exponential function. And the demand that each customer can achieve is related to the pressure and to the nozzle size. So for the different nozzle size at the customer connection points, we have different K values. Now, for the pressure-dependent supply, the methodology of using the pressure-dependent supply through the emitter equation or the orifice equation has been verified on the labs using an experiment, and this experiment was done by Tom Walski. Basically, they have simulated the hydraulic model on a physical system. They used a BVC network of 1 inch in diameter, and they have the tank at the supply node just on the top, and they have 2 outlets. They have simulated outlet B and outlet C, and they have used different patterns for the system, water supply system, either through closing the valves at the green legs, so it acts like a network, a pipe of an S shape, or a grid system. And they have varied the pressure, the head at the supply source, which is the tank at the top of the screen, and they have simulated the orifice at the outlet B and outlet C through using valves and throttling the valves at those 2 outlets through using globe valves to simulate the different sizes of the nozzles at the customer connections. And they have done like 12 combinations using the S-shape model or using the grid value, and either turning the valve at the outlet B on and closing the valve at outlet C, and with using those different combinations and comparing the results of the pressure and the flow at each outlet, outlet B and C, to the result of using a hydraulic model that simulates the same experimental conditions, but through using pressure-dependent demand analysis, they have approached similar values between the theoretical results and the experimental results. So they have achieved an exponential form for the pressure of almost 0.5, as shown on the table, 0.51, 0.52, 0.55. So in the exponential form of the pressure-dependent demand analysis of using the emitter equation of Q is equal K multiplied by P to the power 0.5, it's in good agreement with the experimental results achieved through the model produced on the lab. So as I have stated earlier, in the supply-driven system is a more accurate model to represent the case of intermittent water supply. It can also help the designers to configure the supply-driven systems because using the demand-driven models does not really give a good idea about how the system works in real life. And it is very effective for water equality, pressure, and leakage management. And it can also help in developing schedules for the water supply systems in the different zones. Why this topic is important? Because in this region, And over the world, a lot of customers are on intermittent water supply, as shown in this table. In our region, Middle East and North Africa, more than 75% of the population are on intermittent supply. In Africa, it's 30%. In Asia, it's 50%. In Latin America and the Caribbean, it's 60%. So we have simulated a case study for our project in Jordan. We have distribution zones in Deir Alla. It's a Ma'addi system. And we are using the pressure-dependent demand analysis to simulate the hydraulic conditions. We have compared the behavior of the system using the demand-driven analysis and the pressure-dependent demand analysis. And for example, this figure shows the continuous supply. It shows the results of the continuous supply modeling using the demand-driven analysis. So the people on the high areas, okay, here to the far east of this figure, they experience low pressures because they are located at high areas, and this will become clearer if we use the pressure-dependent demand analysis. So if we are using a peaking factor of 1, we can see that those people who are on high areas are still suffering from low pressures compared to the people on low areas who have high pressures. The pressure ranges between red up to green. The red shows low pressures, the green shows higher pressures. And now for a peaking factor of 2, this means that we are supplying the people with water every other day. And this is for a peaking factor of 3. As we go for with the more the peaking factor, the more the lesser pressure at the high areas, and this is for a peaking factor of 4, 5, and this for the 7, it means that we are supplying people for with their weekly demand in 1 day. So as shown here, most of the system is suffering from lower pressures, but if we relate this to the demand, it shows that people who suffers from low pressure actually also suffers from lower demand. So this shows the deficit in the demand in as a number. So the negative numbers shows that those people are actually getting demand in excess of their need. -3 means that they are at low areas and they are getting more demand, while those people who are on high areas are suffering from less water at their connections, so that they can't fill their tank to be used over the week. And that's it. So thank you.
Thank you, Lupa and Dr. Chen, for this very interesting presentation on intermittent supply and pressure-dependent supply modeling to deal with that. You took me back, I don't know, 30 years, let's say 20 years back to college days. So I'll open the floor for questions. Yes, Zach, right?
Do you think that this model could be used to estimate the risk of cross-contamination within the network for specific nodes?
Actually, okay. So actually, the hydraulic models now, also can model water quality. Okay, for example, your cross, contamination. So we can use tracing. So let's say you have a point salt, point contamination. So you will see when, okay, like how far it reaches, how soon it reaches, how much it reaches. Okay.
Other questions? Please go ahead.
Hi, I was just wondering if...
Could you just, your name?
Oh, my name is David Favaza. I'm with Tetra Tech. I was wondering if you're able to utilize the model to determine exactly how many additional hours or days of supply you would need to serve those customers at higher elevation to ensure that they have equity of supply, and if you can adjust the operational scheme to make that happen.
Exactly, David. That's the purpose. Why we use this one, because the pressure dependent, dependent modeling is more accurate. So we try to equalize, the supply time for the customers. So that way, almost all the customers they will get water within the supply time. So that will solve the water, inequality issue. One of the challenges in the intermittent supply system is, some people get a lot of water, some people they don't get much water, especially in some countries. Okay, they don't have any regulations on the ground storage tanks. So some people they have a huge tank, some people they have little tanks. So through this modeling, so we know how long is needed to supply the customers and how much water they can get, so we can control the system. Also, we can see how we should delineate the DMAs, the zones. Yes.
Thank you. Question?
Salam, Mohammed Faris, consultant engineer. Just I want to ask, is there any impact in energy consumption during this modeling? Did you notice anything there?
Yes, actually that's correct. So actually for the system we are designing, we are going to model the energy consumption, in order to compare the alternatives. Because in Jordan we understand, electricity is very expensive, and it's one of the big burdens on WAJ for Water Authority of Jordan. So definitely yes.
Okay, thanks.
Okay, thank you. Any other questions? We'll open for another round, let's say 5 minutes if you have questions to the other speakers. If not, we'll wrap up. Any dying questions? This is your last chance, last session of the entire week. Okay, one more.
دكتورة